Thank you very much for your introduction. Then I really have a pleasure to share this research and to be with you in this webinar. My presentation is entitled Evolution of Forest Management Planning in Morocco and the Use of AI and Close Remote Sensing Methods to Improve National Forest Inventory. My presentation will follow the following plans: introduction, Morocco forests, global issues, forest management planning evolutions, and I will present the study areas that have been specified for this study, material and methods, result and discussion, and I will finish by a conclusion. As an introduction, we can see that, and we can say that Morocco is really more than 90% of its land. It's suffering from aridity. The bioclimates that is prevalent in Morocco is arid climate, according to the classification of bioclimates. That's the reason for which we came up with the politics and the policy that try to use efficiently the water. That's the reason for which we constructed, and we still constructing some dams in Morocco, trying to save about 60 billion cubic meter of water within the 100 to 130 dam in Morocco. Forest area in Morocco is about 9 million hectares, mainly composed of some, how to say, emblematic species. We can say from them cedar, cork oak, tuya, holm oak, argania, which is one of the trees, the species that exist only in Morocco, from which we are producing some, how to say, services. We also have some junipers, pines, alfalfa, and other species that come from afforestations. For afforestation rate, we do have about 8% of the country which is afforested. And we come in with the policy that tried to preserve biodiversity by creating more than 154 sites for biological and ecological interest, and more than 9 national parks. Then, as you know, in everywhere in the world, the forests are playing many, how to say, many services. They are doing a big things for climate regulation. They, how to say, they play a big role in soil protection, biodiversity preservation, and support for local economy for riparians. All right, then. In Morocco, this forest area, is suffering from one of global issues, which is degradation. For this degradation, there are some direct causes. Mainly, we can say clearing, which take from our forest lands more than 6,000 hectares per year. Overgrazing, which takes 4 times the capacity of our forest. Firewood, that population in, how to say, very high mountain area they are using for their warming. Urbanization also is taking place, some area from forest, and also fire take area from this forest. We do have also some indirect, how to say, causes. We can see set mainly from between them precarity of social context, because the local population, mainly riparian population which lives near the forest, they are taking their advantage from this forest. That's what causes ecosystem fragility. We do have some weakness of forest industry and limited management resources, mainly money. These have as a consequence malfunctioning of the forest ecosystem, loss of biodiversity, and low productivity. Then to overcome these issues and to be able to do the conservation of our forest and make it and also make some its development, we came up, the forest department came up with a new strategy that is mainly based on the National Forest Program, which has as objectives soil protection and water control, contribution to socioeconomic development for forest zone and peri-forest zone, protection of the biodiversity and environment, and the production of wood for industry and craft, and finally produce non-wood forest product, which is mainly important for Moroccan ecosystem and services based on some goods and services. And the approach has to be patrimonial. That means taken some specificity of the territory, and it has as ambition to reverse the degradation process, to go toward the development. The willing is to act with partnership with the local population, and the methods is leading the change gradually, not brusquely. It's this National Forest Program, its objective is also to fight against desertification, and we split up this National Forest Program to a regional program that aims to find more financial means and to raise the capacity of local management decisioner. For this, I just see to give you a glimpse about the evolution of the forest management techniques that have been applied from starting from 1940 to 1970. The main methodology was planned harvesting because the population was very low at this time, and the objective of these methods was mainly intensive harvesting and the creation of the first lodging cooperatives. Between 1970 to 2000, we applied in our forest mainly the temporary forest management methods, and the main objective was this forest management planning methods was timber production and regeneration. But we saw that these methods are not very applicable in Morocco. That's the reason for which we came up with the second generation of forest management planning methods that is mainly participatory and sustainable, that have to apply the sustainable process and management planning methods. And the objective of these methods is mainly timber production, regeneration, involvement of local population, which have been not taken into account in the first kinds of forest management planning, consideration of environmental and social dimensions, and integrated action at the territory scale, because our territory is different, because in Morocco we can go from Sahara to very humid region. Then we have to take this into account for in each region. But we still have some gaps, especially in the area of evaluation of environmental and forest services, and integration of new optimization method and new technology tools in the forest management planning. Within this new strategy, we try to identify some what we call chain or filière in French word, filière of or chain of wood forest product, chain of cork industry, chain of non-wood forest projects. We can sit among them medical and aromatic plants, honey production, mushrooms, and others. We identify also the silvopastoral activity, which have mainly the objective of livestock breeding, and ecotourism and recreation chain. But within each forest management planning, we need inventory, and we do have national inventory and also management inventory. But these inventory methods have been traditionally based on field observation, which can say that in some time they were very good, but now they start to have some gaps, mainly time consuming and very expensive. That's the reason for which we try to improve this the efficiency of our national forest inventory by overcoming the logistical and financial problem, and introduce airborne and terrestrial LiDAR technology. This gives us the hypothesis of our work that have been done in two sites in natural forest stand and also artificial forest stand. And our hypothesis is that integrating airborne and ground LiDAR into national forest and forestry would overcome the limitation of traditional methods and significantly increase the efficiency and the accuracy of data collection. Okay, we conducted this study and the research in two sites. The first site is Maamora Forest, which is located in the northwest of Morocco, mainly, how to say it, containing forest that has mainly based on the cork orc, which is the national stand, Quercus suber, the cork orc, but also we have in this forest some artificial stands made mainly by Eucalyptus, pine, and acacia. This forest is about 134,000 hectares, and within this forest, we choose some plots in which we conducted this research, and these plots are mainly made by eucalyptus, because we conducted this research only in eucalyptus stands, and they have different kind of density, starting from density number 1, which is the most dense stand, to density 3, which is the less dense stand. For Ifran stand, which is the mountain forest, Maamora forest is the how to say, the littoral forest. The forest is not in a mountain, but Ifran forest is located in Atlas mountain. We choose also in this area 4 plots, and this plot was established by the National Forest Inventory Program to be able to do some LiDAR scanning in this area, and to take also the field data from this plots. We choose 2 kinds of plots, 2 plots with the pure stand of cedar, and 2 plots with mixed stand of cedar and holm oak. The methodology that have been applied in these 2 kinds of sites is based mainly on the collecting TLS and DLS or ELS data by using some, how to say, methods in this area, and some tools based on drone and LiDAR. The second phase is the pre-processing and processing. The processing consisted mainly in the alignment between alignment of the 2 kinds of the data, TLS and ELS or ULS data, and the pre-processing mainly consisted of cleaning and eliminating some inconsistent data. After that, we did an estimation of dendrometric attribute, mainly dBH, height, and volume, and we did a comparison between these data that have been driven from LiDAR and drone image with the field dendrometric attribute that have been measured on the field. Then the acquisition of ALS and image data was done. Then for the ALS, we used the Trinity F90 plus LiDAR, and also the flight was done in the altitude of 70 meters with an overlap of 40%. Concerning the imagery, we did the imagery with the same drone, but we put on it a Trinity F90%, the Sony camera, to be able to take the image, and the flight was on the altitude of 100 meters, and the pixel, how to say, accuracy was about 1 centimeter per pixel. And the flight were planned using the key-based 3D program that gives the autonomy of the drone. Pre-processing of ELS or ELS imagery was done. First, we did geolocalization of the images. Then we did the alignment of the ELS data, and then point cloud generation based on the images that have been taken with the camera, and the generation of orthophoto. All of this was done using the AgriSoft Meta Shape software. For the ELS, we did the correction of the drone trajectory and georeferencing of the data using the post-pack software. And we did the generation and the coloring of the point clouds to be able to separate after this pre-processing, to be able to separate the foliage from the wood. And we did this using the yellow scan cloud station. Field data was accurate in the Maamora forest using the plots with the 25 meter of diameter. We also took the tree location acquisition using a GPS, and we measured the circumference, the height, and the volume of each tree in each plot. For TLS data, we also used the 25 diameter plots, and we used the NAV VLX tools. Pre-processing data was done using SateMark software for cleaning the data and also for coloring the data to be able to separate the foliage from the wood. The alignment of ELS, ULS, and TLS point cloud was done using Cyclo 3D software based on the mark on the GPS and the control point on the ground. And the segmentation of individual trees was done using the LiDAR package, which is a program using R languages based mainly on the Delpon and Chrome algorithms. What is based mainly on the crown high models and the local maximum algorithm to be able to individualize trees in, and that's what gave us the stand, which is well individualized here in this figure. We did high extraction using a local maximum filter, and we came up with this. You see in this graph that all the trees have been well identified, and we could also identify the ID of each forest and also its localization in the field. We did also wood foliage separation using mainly the Cloud Compare software. We used in this software mainly the colorimeter segmenter that was able to do the colorage of the foliage and the wood separately, and we come up with this structure giving us the difference between the foliage and the wood. Concerning the extraction of circumference and volume for Maamora data, we used mainly convex Hall functions from R and the LabC package from Python that gave us the ability to extract circumferences and volume. For the different data, we used mainly the QEMS algorithm, which is the 3D geometric representation of the tree built from terrestrial or UAV LiDAR point clouds, where the tree structures is modeled as a set of connected cylinders. And as a result, we can say we got some very interesting results. Mainly, then this is the result from Maamora for Maamora artificial stand. We were able first to do the alignment of the data. Then the first result we can see here, the alignment of TLS and DLS data, which gave us the whole structure and the three-dimensional view of our stand. The tree location and high estimation was done greatly in all the plots in the Maamora forest with precision, with very high precision. And we can see that in the plots 1, 2, and 3, I just want to say that we use it in the plots 1, 2, and 3, both ALS and TLS data. But in the plots 4 and 5, we used only TLS data. We did this to be able to compare between the combined data TLS and DLS, and also only TLS data to estimate some dendrometric attributes. Then we can see here that how to say all in the plots 1 and 2, 3 in which we use both TLS and DLS data, the accuracy were very high. Then the relative how to say relative ERMS was very good. For this, we were using the local tree function from the LiDAR package to be able to calculate this the height of this stem. We see here in this table also that the bias is very low, but it's negative. That can give us the idea that it was a slight underestimation of the height. We can see that the combination of the ALS and TLS is very effective if we combine them for estimating the height. The reliable approach is very good because we used some functions and both these two kinds of data, and we saw that we have some effect on vegetation density, because we saw that in the dense stand, which is I saw that plot 1, 2, and 3, when the plot 2 is the very dense stand, the density 1. There are some effect of the vegetation density on the accuracy of the measurement. Then for the segmentation of individual tree, all the plots were done correctly, which gave us this figure with all the trees well segmented. And you can see here in this animation that the tree was completely well segmented individually, and we separate between foliage and wood. Then for this, we were able to do the separation between the foliage and wood. That you can see in this presentation. And then we came to do the estimation of the circumference of our trees, and we saw here in this table that there is some variability on measurement accuracy between the stand that have been observed mainly in dense part of the stands. We can see here that plot 1 and 2 vary between 0.8 to 1.1, and the relative RMS varied from 1.9 to 4.9, which can be how to say attributed to some difficulty to observe individual trees, mainly in dense stand. The difficulty of scanning tree with high foliage density, that's what gave us this kind of slight higher ERMS in our study. We can also say that also the separation between foliage and wood can give us some loss of information if it's not done correctly. That plot scanned with the TLS alone shows a comparable result to those scanned with TLS and DLS, mainly for the circumferences. For volume estimation, as I said, we used the methods that I explained in the methodology, and we saw that from plot 1 to 3, we have quite high, not very high, but accuracy. But compared to the plots 4 and 5, we do have a near MS less how to say, more than the plot 1 and 4, 2 to 3. Then the ELS integration improve volume estimation accuracy, because in the plot 4 and 5 we use both we use only TLS, but in the plot 1, 2 and 3 we use both TLS and ELS data. Okay, then concerning the accuracy, we can say that the foliage density can play a role in the accuracy and the quality of that references data, because we use it for Maamora forest reference data that we took from the field, but for volume estimation we used an equation that have been made in 2011 according to the last forest management plan. Then 2011 is far from 10 years. It can have some effect on the accuracy of of the data. Concerning IFRAN forest, mainly natural stands, we did the point cloud alignment based mainly on the stable natural markers on the field, on the terrain. As I told you, we use it here 4 plots, 1, 2, 3, and 4, and you saw here the ERMS is very high. We did a refinement of this alignment also using the ACP algorithm. And we can see here that in the plots from 1 to 3, the accuracy were very high, but the plots 4, the accuracy is not very high comparatively to the plots 1 to until 3, because probably of the complex topography and stand density, because the plot 4 is the highest density in between these plots. We use the crown the canopy high model to extract the tree to extract the tree in our plots from plot plots to 4, and using all the the modality. TLS is using just TLS data, ULS or ELS using just ULS data, and UTLS combining the all data and trying to, and we saw here that the results are really accurate and very comparative. Concerning tree segmentation and individualization of tree segmentation, in the plot 1 and we had a detection of more than 50% of trees correctly matched. Why this is? Because in the plot from 1, 2, and 3, the density is not very high, but in the plot 4, the density was very high. We were in the density of category 1, which means that we have more than 60% coverage on the field. And we saw that the segmentation according to the heights is very important, and it's growth with the height of the forest. More high is the forest, more the segmentation is good. We did also the foliage in this stand, this stand and cedar stand. The separation of between the foliage and tree, and we saw in this animation that the separation was done very good. We did this to isolate foliage and the wood part to be able to estimate accurately dBH and volume. And we can see here in this graph that the height using only ULS was very high. In the graph you can see that here we do have a field inventory measurement and the ULS estimated height, and the relation between them is very important, very high, giving us an air square about 1.98. The same case, but now using just TLS, and also here the accuracy is very high, and the relationship between field data and estimated data using TLS is very high. Concerning the same attribute which in the high, but this time we used all the data, aligned data, combined data, TLS and ULS, and we still have here a very good result. Crown diameter was also determined using one time ULS data, the TLS data, and the combined ULS and TLS data, and we find here that the result as very high. We find that the ERMS is not very high, but the relationship between the field data and the estimated data based on the TLS and DLS data are very important. Now we also try to estimate the DBH using two kinds of methods. The first one is just adjustment circle based only in TLS data, try to fit a circle around the trees. And the second method is try to using allometric models. Then for using trying to estimate DBH data using just adjustment circle, we find that the results still very good, more than 60%. Using TLS and DLS data, the results are not very high. We found here that the relationship between DBH on the field and the LiDAR data are quite not good, having an ERMS more than we how they expected. This is because mainly of the density of the stand, giving us the idea that more the dense is the stand, less accurate are the measurement. But using when here we did a separation between small trees and some big trees, and we did the segmentation, and we did this measurement mainly on the trees that are more than 10 centimeter DBH, and we find that it gave us a very important result with the TLS fit. That means the TLS that have been used just with adjustment of a circle around the trees. And for this result, we can see here that for the DBH for the tree that more than 10 centimeters, the results are very good, and the relationship is more than effective. How to say, it is about 1.9, and the RMS is low. The same case using UTLS, then combining the data of ELS and TLS. Using also allometric methods, we find that the results are good. The R square between the field data and the LiDAR data is about 170, which can give us the idea that we can use this predicted model to be able to estimate DBH. Comparing our result to other study that have been done before, we found that our study is very comparative and sometimes more effective than the other studies that have been done by other authors and by researchers. For the volume, we found that the results are very important, that very high, using TLS or both combined data, ULS and TLS, and we found here that the R square is about 1.9 in both situations. Taking into account our result and compared our result with other authors, that we found that our results are also comparative and in some time are better than the studies that have been done by Bornald or Fan and Olds on Takujo. We also try to take and to measure to estimate also the basal area, and we found that this measurement using TLS and ULS data are very performant, and we can say that we can use it for effectively in different kind of stand, natural and artificial. As a conclusion, we can say that the contribution of the ALS+TLS data are very important for estimating dendrometric analysis, for estimating dendrometric attribute, doing some dendrometric analysis based on using some algorithm and some program that have been driven mainly from our package. The accuracy of measurements are very high. And the influence of foliage density can sometimes influence the accuracy, because the signal of the LiDAR data can suffer from some complexity of penetration to the stand. And there is these methods we found that is very potential because it's take less time on the field, and it's less, how to say, less expensive than the data that we could have mainly based on the field process. Here we have this table that give us the how to say, the main result. We can find out the high can mainly and significantly driven from ALS/ULS data. Using this data, we can calculate the height. For the DBH, we can mainly use the TLS data, and for ground diameter, we can use both of them, ALS and TLS data. Also for the volume, we can use both of them, TLS and TLS data, and also the basal area. But this study still suffer from some limitation. We have to find a good way to overcome the complexity of the foliage density. We have to look for good data in the field, and to construct a model that are new for estimating the volume. For example, the volume estimation methodologies have to be very accurate to be able to have more accurate data, more accurate results. And mainly in the stand that they have big, how to say, understory, this can play how to say, a negative effect on estimating circumference and the separation between foliage and wood. That's it for my presentation. I would like to thank you for your presence, and I'm still here with you if you have any question.